So, basic solidification mode in welding process can be represented in four different ways. One is that planar, that means the solidification front move in the form as a plane. Next, another mode of the solidification front that can create maybe by breaking the planar interface, and it can create the kind of cellular structure. Okay. And then during the solidification also, that there may be the possibility of formation of the another type of solidification mode, that is called columnar dendritic structure. That means, the growth happens in such a way that it makes a big column and the primary and secondary dendritic arms attached with that column. So, this kind of structure also it is obvious from the figure that this structure actually represents the columnar dendritic type structure, and that actually happens during the solidification from the within the liquid metal transformed to the solid phase. So, during that transformation it creates this kind of that means columnar dendritic structure. Of course, the dendritic structure can be formed in the like a equiaxed kind of structure. That means, it is like if you see the from the figure that there is a 3 arm and the secondary dendritic arm are spacing accordingly. So, that it looks like the equal amount of spacing in all 3 directions. So, it is a kind of structure or mode is kind of a equiaxed structure, microstructure, what you can say almost equal size of the grains throughout the microstructure. So, these are the 4 different types of solidification mode generally observed in case of welding process. Now, in much details solidification in welding process, and it is very much specific to that the alloy materials, basically solidification of the not pure metal. So, maybe we can say that in case of alloy metal, that constitutional supercooling is the one of the important phenomena that is attached with the solidification during the welding process. So, supercooling, we have some idea that from when during the solidification, that when the liquid molten metal comes around the phase transformation temperature, that means from solid to liquid phase transformation temperature. So, during that transformation, and there is a amount of the supercooling observed in the liquid metal. Of course, it pertains with some conditions, that means that before starting of the phase change, the amount, the nucleation mechanism involved in the welding process or maybe solidification process, that actually governed by the what is the amount of the supercooling temperature. That means, the supercooling temperature below the solid to liquid transition temperature. So, in case of pure metal, it can be well defined from the time versus temperature diagram, and this amount of supercooling depends on the, or maybe values are the different for the different types of the material. So, normally the amount of the supercooling is mainly promote that the homogeneous nucleation, or maybe in case of homogeneous nucleation for in solidification process is mainly driven by the amount of the supercooling, which is entirely different from the heterogeneous nucleation mechanism. But constitutional supercooling can be defined in such way that it actually occurs during solidification and due to the compositional solid changes, which finally result in the liquid metal below the freezing point temperature, and that exists ahead of the solid liquid interface. Actually, this constitutional supercooling mainly affects or better describes the what is the amount of the supercooling that depends on the compositional solid changes, specifically for the alloy material, and that amount of the solidification constitutional supercooling during the solidification in case of graphically we can represent here that this region marked by red color that actually represents the region of the constitutional supercooling, or we can say the amount of the supercooling in case of alloy. But this amount of the supercooling generally exists during the solidification process of specifically the alloy metal, but the mathematical term or parameters that actually govern or may be linked with the constitutional supercooling is that is better described by the one is the diffusion coefficients of the solute in the liquid. That means, this dl that represents the diffusion coefficients. If you see the unit of the diffusion coefficient is the length square per unit time. So, mainly it is a diffusibility, it represents the diffusibility of the solute in the liquid metal. Another parameter that actually used to describe the solidification behavior specific for the alloy material, that is the growth rate. So, that is the unit is that length per time or length per unit time, that is representation of the growth rate, and then temperature gradient. So, temperature gradient is the theta by L, that means, it is the temperature per unit length. So, these are the typical parameters that actually involve to represent the constitutional supercooling during the solidification process. Now, we try to explain this phenomena graphically. That first, if we look into this first figure, there is a transition of the solid to liquid phase. So, here the growth rate is R, that means, growth rate more it is linked that what is the what way that the solid liquid interface is basically moving. So, that zone between the solid and liquid, there is a zone mainly that is called the Mossi zone. So, in this zone the liquid and the solid phase coexists, but this depends on the or in the amount of the supercooling exists within the during the solidification of a specific alloy. Now, if we see the temperature versus concentration graph, here you can see the solidus line is there and then liquidus line and initial composition having the C0. So, this material is subjected to some amount of the supercooling. So, that constitutional supercooling is simply marked by the red color, and that means the temperature difference in this case is delta T. So, that delta T on the temperature axis, it is represented that between the TL and TS, that is the amount of the temperature decrement with respect to the initial composition. And if we see even with respect to on the liquidus line, the composition or concentration of the alloy material, here you can see that C0 by K, that is we represent that C that K equal to ratio of the CS and C0. So, from here we can this here composition is represented by C0 by K. Now, this amount of the constitutional supercooling, if we project in the right hand side figure, here if we see temperature versus distance from solid liquid interface. So, up to what extent from the interface it can go, that is represented simply just projecting this constitutional supercooling on the time versus concentration graph to the time versus distance graph. Here we can see that this is the on the this first slope is the actual slope. The actual slope is the temperature gradient represented by the mathematically represented by term Z, temperature gradient. And then if we look into the other slope, the slope of the tangent at this point, here we can see the slope of the tangent can be represented by what is the slope means, the change of the temperature, that means temperature difference with respect to some distance here, but here the distance can be counted maybe in terms of the boundary layer here, that is the diffusivity or DL, diffusion coefficient divided by the growth rate. If you see the dimensionally also, so this term delta T and DL by R, that also represents the slope of the tangent. So, in this case it is very obvious that definitely the actual slope from the figure also it is very clear, the actual slope g is less than equal to the slope of the tangent. That point of view we have estimated that during the supercooling what is the temperature difference and what is the amount of the distance travelled by the solid liquid interface in terms of the diffusivity and growth rate. So, here if you geometrically or graphically we can see this slope is basically less than that of the estimated slope here. So, to have the constitutional supercooling, so graphically we can say that this condition G by R less than delta T by dl, this condition is satisfying. So, that actually that is the mathematical conditions during the solidification. So, probably having in this case the constitutional supercooling. So, now we will further look into other condition, or maybe we try to explain physically that what is the mathematical condition for the constitutional supercooling and how it can be linked with the solidification behavior during the welding process. So, first comments is that of course, the shaded area that represents the constitutional supercooling, therefore, that region is consist of actually liquid alone is unstable. So, in that zone basically solid and liquid coexists. Now, to estimate that slope also we assume that the thickness of the boundary layer during the movement of the solid liquid interface at the steady state condition is better described by the dl by r. dl is the diffusivity divided by the growth rate, and that dimensionally it represents the length, dimensionally it represents in terms of length dl by r. Now, to avoid constitutional supercooling, we can put the condition just reverse having the constitutional supercooling. So, having the constitutional supercooling, this was the condition G by R less than delta T by dl. What to avoid constitutional supercooling, it is just G by R should be greater than equal to delta T by dl. These are the to avoid the constitutional supercooling. So, this mathematical condition is sometimes helpful to quantitatively explain the solidification behavior, that what are the driving mechanism whether constitutional supercooling exists or not. Based on that type of nucleation, whether it is homogeneous and heterogeneous nucleation, that is better explained by these mathematical conditions. Now, the constitutional supercooling can also be explained in can also be used to explain whether there is a need or breakdown of the solid liquid interface can be stable interface from the planar solid liquid interface. That means, planar solid liquid interface is stable if not having the constitutional supercooling, that means just opposite to the condition of the avoiding the constitutional supercooling. So, in that sense G by R greater than equal to delta T by L, that actually represents for the stability of the planar solid liquid interface. Now, in planar solid liquid interface it may break also, and due to the cellular or maybe in the dendritic. So, that solid cell or dendritics actually can coexist with the intercellular spaces or interdendritic liquid. So, that breakdown of the planar solid liquid interface to other solidification mode, cellular type or dendritic type, that dendritic type, that can be explained mathematically here also in terms of this G, R, delta T and dl or these parameters. So, higher G and lower R, that actually leads to the planar solid liquid interface. That means, if we look into the condition also that G by R ratio is very high, that means there is a existence of the solidification mode in terms of the planar solid liquid interface. Other side, higher delta T, that means temperature difference is very high. So, that means degree of supercooling is very high, and of course, more amount of the diffusivity dl, that actually leads to the more difficulty for a planar solid liquid interface to be stable. So, that actually breaks down the stability of the solid liquid planar interface during the solidification process. So, here we can say mathematically that two things, if G by R less than delta T by dl, that means there is a existence of the constitutional supercooling, that means non existence of the planar solid liquid interface in this case. Other way also, if G by R is greater than delta T by dl, that means there is a existence of the, or that is a favorable condition to put the solidification mode in terms of the planar solid liquid interface. Now,